Chapter 1. Introduction. The weirdness begins. While humanity has spent decades dreaming of walking on Mars, the most alien worlds in our solar system have been hiding in plain sight, orbiting the gas giants in the outer reaches of our cosmic neighborhood. In just the past year alone, discoveries from NASA's Juno mission, the Hubble Space Telescope, and ground-based observatories have completely revolutionized our understanding of these distant moons, revealing them to be far more active, complex, and downright weird than we ever imagined. Consider this. Whilst our moon is a relatively quiet, geologically dead world that's been essentially unchanged for billions of years, the moons of Jupiter, Saturn, Uranus, and Neptune are volcanic hellscapes with subsurface furnaces, worlds with more liquid water than all of Earth's oceans combined, moons that have been knocked off their axes by cosmic catastrophes, and satellites covered in alien dust that accumulates like bugs on a windshield. The discoveries we'll explore today span from Jupiter's volcanic moon Io, where NASA's Juno spacecraft has revealed an underground network of cooling lava flows covering 10% of the moon's surface, to Saturn's incredible collection of 274 moons, 128 of which were discovered just this past March. We'll journey to Uranus, where the Hubble Space Telescope has uncovered a cosmic dust mystery that's completely upended our understanding of how magnetospheres interact with moons, and we'll visit the most distant frontier at Neptune, where future missions may finally unlock the secrets of the solar system's edge. What makes these worlds so fascinating isn't just their exotic nature, it's the intricate orbital mechanics that drive their activity. Tidal forces, orbital resonances, and gravitational interactions create a cosmic ballet that generates enough energy to melt ice, drive volcanic eruptions, and maintain liquid oceans beneath frozen surfaces. These aren't just dead rocks orbiting giant planets, they're dynamic worlds that may harbor the conditions necessary for life itself. Chapter 2. Jupiter's volcanic hellscape, Io's underground furnace. Our journey begins at Jupiter, where NASA's Juno mission has been peering beneath the surface of the most volcanically active world in the solar system. In April 2025, the Juno team published findings that have fundamentally changed our understanding of Io's internal structure and volcanic processes. Using the spacecraft's microwave radiometer and Jovian infrared auroral mapper, scientists have created the first ever subsurface temperature profile of this hellish moon. The results were staggering. Shannon Brown, a Juno scientist at NASA's Jet Propulsion Laboratory, described the team's surprise when we incorporated the microwave radiometer data with JIRAM's infrared imagery. We were surprised by what we saw, evidence of still warm magma that hasn't yet solidified below Io's cooled crust. At every latitude and longitude, there were cooling lava flows. This discovery reveals that approximately 10% of Io's surface sits atop a network of slowly cooling lava flows just beneath the crust. It's a finding that helps explain one of Io's most puzzling characteristics, how this relatively small moon with a radius of just 1,821 kilometers manages to completely resurface itself every few thousand years through volcanic activity. The mechanism driving this incredible volcanic activity lies in Io's orbital relationship with Jupiter and its neighboring moons. Io completes an orbit around Jupiter every 1.77 Earth days, locked in a 2, 1 orbital resonance with Europa, and a 4, 1 resonance with Ganymede. This gravitational dance creates a phenomenon known as tidal heating, where the constant flexing of Io's interior due to varying gravitational forces generates enormous amounts of heat through friction. To put this in perspective, Io experiences tidal forces roughly 6,000 times stronger than those Earth experiences from our moon. The moon's elliptical orbit means it's sometimes closer to Jupiter and sometimes farther away, causing the tidal bulge to shift back and forth across Io's surface. This constant kneading of the moon's interior generates enough heat to maintain a partially molten mantle and drive the most intense volcanic activity in the solar system. The Juno mission has also tracked individual volcanic events with unprecedented detail. The most energetic eruption in Io's recorded history was first identified during a December 27, 2024 flyby, and was still actively spewing lava and ash as recently as March 2025. This single eruption demonstrates the incredible longevity of Io's volcanic processes, with some events lasting months or even years. Brown's team describes Io's volcanic system as functioning like a car radiator efficiently moving heat from the interior to the surface, cooling itself down in the vacuum of space. This analogy perfectly captures the moon's role as a heat engine, constantly transferring thermal energy from its tidally heated interior to space through volcanic eruptions and lava flows. Understanding how tidal heating works in such an extreme environment provides crucial insights into similar processes occurring on other moons throughout the outer solar system, where subsurface oceans are maintained by the same fundamental physics that drive Io's volcanic fury. Chapter 3: Europa's Hidden Ocean, the Search for Life. Whilst Io represents the extreme of volcanic activity, its neighbor Europa embodies a different kind of dynamism, one that may be even more significant for the search for life beyond Earth. In October 2024, NASA launched the Europa Clipper mission, humanity's first dedicated probe to investigate the habitability of this ice-covered ocean world. The mission represents a culmination of decades of tantalizing hints that beneath Europa's frozen surface lies an ocean containing more liquid water than all of Earth's oceans combined. Recent observations have revealed that Europa's icy surface is in constant flux, with new research published in May 2025 showing that ice crystallization patterns on the moon's surface provide direct evidence of the dynamic ocean beneath. The constantly changing ice formations suggest active circulation within the subsurface ocean, driven by the same tidal forces that power Io's volcanoes, but manifesting in a completely different way. Europa's orbital mechanics tell a fascinating story of gravitational choreography. The Moon orbits Jupiter every 3.55 Earth days, maintaining a 2:1 orbital resonance with Io. For every 2 orbits Io completes around Jupiter, Europa completes exactly 1. This resonance, combined with Europa's slightly elliptical orbit, creates tidal flexing that generates enough heat to maintain a liquid ocean beneath an ice shell estimated to be 15 to 25 kilometers thick. The physics of this process are elegant in their simplicity, yet profound in their implications. As Europa moves closer to and farther from Jupiter during its elliptical orbit, the planet's immense gravitational field stretches and compresses the Moon's interior. This constant deformation generates heat through friction, preventing the subsurface ocean from freezing solid despite Europa's surface temperature of -180 degrees Celsius. What makes Europa particularly intriguing for astrobiology is not just the presence of liquid water, but the potential for the ocean to interact with the rocky mantle below. This interaction could provide the chemical ingredients necessary for life, including dissolved minerals and potential energy sources. The Europa Clipper mission, arriving at Jupiter in 2030, will use ice-penetrating radar to map the ocean's depth and composition, potentially revealing whether this alien sea could support life. The mission will also investigate one of Europa's most mysterious features, the linear ridges and chaotic terrain that crisscross its surface. These features, some stretching for thousands of kilometers, are thought to be caused by the movement of the subsurface ocean, creating pressure that cracks the ice shell from below. Understanding these processes will help scientists determine how material from the ocean might reach the surface, where future missions could potentially sample it for signs of life. Recent modeling suggests that Europa's ocean may be stratified, with different layers having varying compositions and temperatures. The deepest parts of the ocean, in contact with the rocky mantle, could be warm enough and chemically rich enough to support hydrothermal vent systems similar to those that harbor life in Earth's deep oceans. These environments represent some of the most promising locations for extraterrestrial life in our solar system. The Europa Clipper mission will conduct 49 close flybys of the Moon, using its suite of 9 scientific instruments to build a comprehensive picture of Europa's habitability. The spacecraft will map the ice shell's thickness, analyze the ocean's composition, and search for plumes of water vapor that might be erupting from the surface, similar to those discovered on Saturn's moon Enceladus. Whilst Europa and Io showcase the ongoing effects of tidal forces, Jupiter's largest moon, Ganymede, tells a story of catastrophic violence from the early solar system. In September 2024, researchers published a groundbreaking study revealing that Ganymede was struck by a massive asteroid approximately 4 billion years ago, an impact so powerful it completely reoriented the Moon on its axis. The asteroid responsible for this cosmic catastrophe was approximately 300 kilometers in diameter, roughly 20 times larger than the Chicxulub impactor that ended the age of dinosaurs on Earth. To put this in perspective, if such an object struck Earth today, it would likely sterilize the entire planet's surface. But Ganymede, being much larger than Earth's moon, with a diameter of 5,268 kilometers, survived this tremendous impact and bears the scars to this day. The evidence for this ancient collision lies in Ganymede's unique surface features, particularly a series of parallel grooves and ridges known as furrow systems that extend across much of the moon's surface. By analyzing these features and working backward through computer modeling, researchers determined that only an impact of this magnitude could have created the observed geological structures. What makes this discovery particularly remarkable is the timeline of Ganymede's reorientation. The research suggests that after the impact, Ganymede gradually shifted to its new orientation over approximately 1,000 years due to tidal dissipation, the same process that causes Earth's moon to gradually move away from our planet. This relatively rapid reorientation demonstrates the incredible power of the impact and the dynamic nature of gravitational interactions in the early solar system. Ganymede's story becomes even more intriguing when we consider its current status as the largest moon in the solar system and the only moon known to have its own magnetic field. This magnetic field, generated by a liquid iron core, creates a magnetosphere that interacts with Jupiter's much larger magnetic field in complex ways. The ancient impact may have played a role in shaping Ganymede's internal structure, potentially affecting the convection patterns in its core that generate this unique magnetic field. The European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, launched in April 2023, will provide unprecedented insights into Ganymede's structure and history when it arrives at Jupiter in 2031. JUICE will become the first spacecraft to orbit a moon other than Earth's moon when it enters orbit around Ganymede in December 2034. The mission will use radar to probe beneath Ganymede's surface, potentially revealing how the ancient impact affected the moon's internal structure and the subsurface ocean that likely exists beneath its icy crust. The early solar system was a chaotic place, with large impacts occurring regularly as planets and moons swept up the remaining debris from the solar nebula. Understanding how Ganymede survived and evolved after such a catastrophic event provides insights into the resilience of planetary bodies and the processes that shaped the architecture of our solar system. This ancient impact also raises intriguing questions about Ganymede's potential habitability. Like Europa, Ganymede is thought to harbor a subsurface ocean beneath its icy crust. The energy from the massive impact 4 billion years ago may have had long-lasting effects on this ocean's chemistry and circulation patterns, potentially creating unique conditions that could have influenced the development of any life that might exist there. Chapter 5: Saturn's Moon Explosion, 274 and counting. If Jupiter's moons showcase individual extremes of geological activity, Saturn's moon system represents something entirely different. A cosmic explosion of diversity that has recently reached almost incomprehensible proportions. On March 11, 2025, the International Astronomical Union announced the discovery of 128 new moons orbiting Saturn, bringing the ringed planet's total moon count to a staggering 274, more than all other planets in the solar system combined. This discovery, led by Edward Ashton of the Academia Sinica in Taiwan and Brett Gladman of the University of British Columbia, represents the largest single addition to any planet's moon system in astronomical history. The team used the Canada-France-Hawaii telescope atop Mauna Kea to identify these previously unknown satellites, all of which fall into the category of irregular moons, small distant objects in highly eccentric and inclined orbits. These newly discovered moons are remarkably small, ranging from just 1.2 to 1.8 miles, 2 to 3 kilometers in diameter. To put this in perspective, you could fit several of these moons inside a typical Earth city. They're potato-shaped rather than spherical, lacking sufficient mass for their own gravity to pull them into round shapes. In many ways, they resemble Mars-captured asteroid moons Deimos and Phobos more than traditional moons like our own. What makes this discovery particularly fascinating is not just the number of new moons, but what their existence tells us about Saturn's violent past. The research team's analysis suggests that these 128 moons, along with many of Saturn's previously known irregular satellites, are the fragments of a much larger moon that was destroyed in a cosmic collision sometime within the past few 100 million years. Brett Gladman explained to researchers that a large fraction of the 128 moons' orbits strongly support the idea that a larger moon was destroyed at most 100 million years ago. The collision could have been more recent than that, it just can't be older, or all these small moons would have been running into each other and disappearing. This timeline constraint is crucial for understanding the dynamics of Saturn's moon system. If the collision had occurred much earlier, the resulting fragments would have had time to collide with each other and coalesce or be ejected from the system entirely. The fact that we still see these small moons today suggests that Saturn experienced a major collision event in the relatively recent astronomical past. The orbital characteristics of these moons provide additional clues about their origin. Many of them share similar orbital inclinations and eccentricities, suggesting they originated from the same parent body. However, some groups are too dispersed to be explained by a single collision, leading researchers to propose either multiple independent collisions or second-generation impacts between fragments of the original collision. The discovery process itself represents a triumph of modern astronomical techniques. The team had to distinguish these faint moving objects from the millions of background stars and galaxies visible in their images. Each potential moon had to be tracked across multiple nights to confirm its orbit around Saturn, a process that required sophisticated computer algorithms and careful analysis of subtle brightness variations. This explosion in Saturn's moon count raises intriguing questions about the naming conventions for celestial bodies. Saturn's largest moons are named after titans from Greek mythology, but as discoveries accumulated, the naming expanded to include Gallic, Norse, and Canadian Inuit deities. With 128 new moons to name, astronomers may need to develop entirely new naming conventions. The implications of this discovery extend beyond Saturn itself. Similar collision events likely occurred throughout the outer solar system, suggesting that the current populations of irregular moons around all the gas giants may be the remnants of ancient catastrophes. Understanding these processes helps us piece together the violent history of the early solar system and the ongoing evolution of planetary systems. Chapter 6. Titan's Methane World. An alien Earth among Saturn's vast collection of moons, one stands out as perhaps the most Earth-like yet utterly alien world in our solar system. Titan, Saturn's largest moon, is the only place beyond Earth known to have stable liquids on its surface, but instead of water, these lakes and rivers are filled with liquid methane and ethane. In October 2024, researchers made a discovery that fundamentally changed our understanding of this bizarre world. Titan possesses an insulating, methane-rich crust up to 6 miles thick that may explain both its alien surface and its potential for harboring life. This groundbreaking research, published in the Planetary Science Journal by a team from the University of Hawaii, began with a puzzling observation. Titan's impact craters are hundreds of meters shallower than expected, and only 90 craters have been identified on the moon's surface, far fewer than should exist on a world of Titan's age and size. Lauren Schurmeyer, the study's lead author, explained, "This was very surprising because, based on other moons, we expect to see many more impact craters on the surface and craters that are much deeper than what we observe on Titan." The answer to this mystery lies in Titan's unique composition. The research team discovered that methane gas is trapped within Titan's water ice crust, forming what's known as methane clathrate, a crystalline structure where methane molecules are caged within a lattice of water ice. This methane clathrate crust, ranging from 3 to 6 miles thick, acts as an insulating blanket that warms the underlying ice shell and causes rapid topographic relaxation. The implications of this discovery are profound. The methane clathrate crust makes Titan's subsurface ice shell warm and ductile, causing impact craters to relax and shallow at a rate comparable to fast-moving glaciers on Earth. This process explains why Titan's surface appears so young and crater-poor, despite the moon's ancient age of 4.5 billion years. Titan's methane cycle represents one of the most complex atmospheric and surface processes in the solar system. The Moon's thick atmosphere, composed primarily of nitrogen with about 5% methane, drives a hydrological cycle remarkably similar to Earth's water cycle. Methane evaporates from surface lakes, forms clouds in the atmosphere, and falls as rain, carving river channels and filling lakes in an endless cycle. The orbital mechanics that govern Titan are equally fascinating. The Moon orbits Saturn every 15.95 Earth days at a distance of 1.2 million kilometers, locked in a 3-4 orbital resonance with the smaller moon Hyperion. This resonance, combined with Titan's substantial atmosphere, creates complex tidal interactions that may contribute to maintaining the Moon's subsurface ocean. What makes Titan particularly intriguing for astrobiology is the possibility that its warm, convecting ice shell could transport potential biomarkers from the subsurface ocean to the surface, where they could be detected by future missions. Schurmeyer noted, "If life exists in Titan's ocean under the thick ice shell, any signs of life would need to be transported up Titan's ice shell to where we could more easily access or view them with future missions. This is more likely to occur if Titan's ice shell is warm and convecting." The discovery of Titan's methane clathrate crust also has implications for understanding climate change on Earth, Schurmeyer explained. Titan is a natural laboratory to study how the greenhouse gas methane warms and cycles through the atmosphere. Earth's methane clathrate hydrates, found in the permafrost of Siberia and below the Arctic sea floor, are currently destabilizing and releasing methane. So, lessons from Titan can provide important insights into processes happening on Earth. NASA's Dragonfly mission, scheduled to launch in July 2028 and arrive at Titan in 2034, will provide unprecedented opportunities to study this alien world up close. The nuclear-powered quadcopter will fly through Titan's thick atmosphere, landing at multiple sites to analyze the Moon's surface composition and search for signs of past or present life. Dragonfly will specifically investigate the Selk crater, where the impact may have created conditions favorable for prebiotic chemistry. Titan represents a unique case study in planetary evolution, demonstrating how different initial conditions and orbital environments can create worlds that are simultaneously familiar and utterly alien. Its methane-based weather systems, organic chemistry, and potential subsurface ocean make it one of the most promising locations in the solar system for understanding the conditions that might give rise to life beyond Earth. Chapter 7. Enceladus, the geyser moon's alkaline secrets. Whilst Titan captures attention with its alien landscapes, Saturn's small moon, Enceladus has quietly become one of the most promising locations for finding life beyond Earth. Recent discoveries in 2025 have revealed that this icy moon's subsurface ocean is more alkaline than previously thought, a finding that could significantly impact our understanding of its habitability and the search for extraterrestrial life. Enceladus, with a diameter of just 504 kilometers, is small enough to fit within the borders of Arizona, yet it harbors a global ocean beneath its icy crust that may contain more than twice the volume of water found in all of Earth's oceans. The Moon's most spectacular feature is the series of geysers erupting from its south polar region, discovered by the Cassini spacecraft in 2005. These plumes shoot water vapor, ice particles, and organic compounds hundreds of kilometers into space, providing direct access to the subsurface ocean's contents. The latest research on Enceladus's ocean chemistry suggests that the pH levels are higher than previously estimated, creating a more alkaline environment. This discovery is significant because alkaline conditions can affect the stability of organic molecules and the types of chemical reactions that might support life. On Earth, many extremophile organisms thrive in alkaline environments, suggesting that similar conditions on Enceladus might be conducive to life. The source of Enceladus's geological activity lies in its orbital relationship with Saturn and its neighboring moons. Enceladus orbits Saturn every 1.37 Earth days, locked in a 2-1 orbital resonance with the larger moon Dione. This resonance creates tidal forces that flex Enceladus's interior, generating heat through friction and maintaining the subsurface ocean in liquid form, despite the moon's surface temperature of -201 degrees Celsius. Recent analysis of Cassini data has provided new insights into the connection between Enceladus's geysers and its subsurface ocean. Researchers now believe that the plumes may provide direct access to the ocean itself, rather than coming from a shallow subsurface reservoir. This means that future missions could potentially sample the ocean's contents simply by flying through the plume material, making Enceladus one of the most accessible ocean worlds for astrobiological investigation. One of the most intriguing recent observations involves a mysterious dark spot on Enceladus's surface that appeared to fade over time. Scientists believe this disappearing feature was gradually covered by deposits from the Moon's own ice plumes, demonstrating the dynamic nature of Enceladus's surface and the ongoing interaction between its geological activity and surface features. The chemical composition of Enceladus's plumes has revealed a complex mixture that includes water vapor, carbon dioxide, methane, ammonia, and various organic compounds. The presence of molecular hydrogen in the plumes is particularly exciting, as it suggests hydrothermal activity on the ocean floor where water interacts with rock, similar to the hydrothermal vents on Earth that support thriving ecosystems independent of sunlight. The discovery of silica nanoparticles in the plume material provides additional evidence for hydrothermal activity. These particles can only form under specific temperature and pressure conditions that exist where hot water interacts with rocky material on the ocean floor. This process not only provides energy for potential life, but also supplies essential minerals and nutrients that could support biological processes. Future missions to Enceladus are being planned to take advantage of the Moon's accessible plumes. The proposed Enceladus Orbilander mission would orbit the Moon and eventually land on its surface, providing detailed analysis of the plume composition and surface features. Such a mission could definitively answer whether Enceladus harbors life by directly sampling the ocean's contents through the natural plume activity. Chapter 8: Uranus, the tilted giant's surprising moons. As we journey farther from the Sun, we encounter Uranus, a world so unusual that it literally rolls on its side as it orbits the Sun. This ice giant, tilted at 98 degrees relative to the plane of the solar system, presents unique challenges for understanding its moon system. Recent discoveries in 2024 and 2025 have revealed that Uranus's moons are far more complex and active than previously thought, harboring potential subsurface oceans and displaying unexpected surface processes. The most groundbreaking discovery came in October 2024, when researchers announced that Miranda, Uranus's smallest major moon, may harbor a subsurface ocean beneath its heavily cratered surface. This finding, published by a team from the University of North Dakota and Johns Hopkins Applied Physics Laboratory, challenges our assumptions about which moons can maintain liquid water in the outer solar system. Miranda is a geological puzzle. The few images captured by Voyager 2 in 1986 show a surface that looks like a cosmic Frankenstein's monster, a patchwork of different terrains including grooved regions, rough scarps, and heavily cratered areas, all stitched together in seemingly random patterns. Most researchers initially attributed these features to ancient tidal heating, but the new analysis suggests something far more intriguing. By reverse engineering Miranda's surface features and working backward to determine what internal structure could have created them, the research team discovered that the observed geology could only be explained if Miranda had a vast subsurface ocean 100 to 500 million years ago. This ocean would have been at least 100 kilometers deep, hidden beneath an icy crust no more than 30 kilometers thick. Given that Miranda has a radius of just 235 kilometers, this ocean would have filled almost half of the Moon's interior volume. The key to creating and maintaining such an ocean lies in orbital resonances. Computer simulations suggest that Miranda and its neighboring moons were once locked in orbital resonances similar to those seen in the Jupiter system, creating tidal forces strong enough to heat Miranda's interior and maintain liquid water. What makes this discovery particularly exciting is that the ocean may still exist today. If Miranda's ocean had completely frozen, it would have expanded and created specific types of surface cracks that aren't observed on the Moon. The absence of these features suggests that Miranda is still cooling and may retain a thin subsurface ocean even now. Meanwhile, the Hubble Space Telescope has been making its own surprising discoveries about Uranus's moon system. In June 2025, astronomers published findings that completely overturned expectations about how Uranus's magnetosphere interacts with its largest moons, Ariel Umbriel, Titania, and Oberon. Scientists expected that charged particles from Uranus's magnetosphere would preferentially darken the trailing hemispheres of these tidally locked moons, similar to processes observed at other planets. Instead, Hubble's ultraviolet observations revealed the opposite. The leading hemispheres of the outer moons Titania and Oberon are darker and redder than their trailing sides. The explanation for this cosmic mystery lies in a process that researchers describe as being like bugs hitting a windshield. Dust from Uranus's irregular satellites, constantly bombarded by micrometeorites, creates a cloud of debris that slowly spirals inward towards the planet. The outer moons, Titania and Oberon, sweep through this dust cloud, accumulating material primarily on their leading hemispheres as they orbit. This discovery reveals that Uranus's magnetosphere may be more quiescent than previously thought, or that the interactions between the magnetic field and the moons are more complex than current models predict. The outer moons effectively shield the inner moons Ariel and Umbriel from this dust bombardment, which explains why their hemispheres show similar brightness levels. Richard Cartwright, the study's principal investigator, noted the broader implications. We see the same thing happening in the Saturn system, and probably the Jupiter system as well. This is some of the first evidence we're seeing of a similar material exchange among the Uranian satellites. The study of Uranus's moons is particularly challenging because of the planet's extreme distance and unusual orientation. Uranus's 98-degree axial tilt means that its magnetosphere and moon system are oriented unlike any other planet in the solar system. During Voyager 2's flyby in 1986, the magnetosphere was tilted about 59 degrees from the orbital plane of the satellites, creating a complex and dynamic environment that we're only beginning to understand. These recent discoveries about Miranda's potential ocean and the dust dynamics affecting Uranus's moons highlight how much we still don't know about the outer solar system. Future missions to Uranus, potentially launching in the 2030s during a favorable planetary alignment, could revolutionize our understanding of this unique system and its potential for harboring life in unexpected places.